The students are working really hard today for their presentations. So it's challenging to give a presentation in 10 minutes, I guess. I need to guess the title. I know what DDM is, but I don't know what SPRT is. So let Tammy explain this to us.
Okay, sorry guys. So I completely changed my second talk because seeing how people love the DDM from the first talk. Yeah, so let me start by refreshing people's memory about the DDM model I talked about last time. So the basic idea of the DDM is that when the brain is making a decision between two alternatives, the decision-making process can be modeled as a particle drifting between two bounds, and the drift is driven by the evidence, noisy evidence. So the whole process can be conceptualized as the accumulation of momentary evidence over time until a certain bound is reached. So the reason we really like DDM model is that first, it's very simple mathematically. There's a lot of already existing studies, I mean the mathematical study, including the physics studies, how particle could drift in the space that we can just directly borrow. And secondly, the model could capture both the animal and human behavior very well, and the neural response in the brain very well. And that's actually very rare in the field of computational neuroscience, that we have such a nice model that can both explain behavior and neural response super well. But there's one thing that I've never said about the DDM model. So here in the model, you can see the x-axis is the time, right? It shows you how evidence is accumulated over time. But I never talk about what exactly is y-axis, right? In the DDM model, the y-axis is just some abstract concept of evidence. So we want to ask the question, what exactly is the y-axis in the brain? When the brain is accumulating evidence, how can we quantify evidence? So that's a question I'm going to talk about today. So we can frame our question this way. There are two hypotheses we want to test, and when we receive a piece of evidence, how do we decide whether this evidence is good for hypothesis 1 or hypothesis 2? And the way we can do this is we can compute two conditional probabilities. What's the probability of H1 is true given we see evidence? Or what's the probability of H2 is true given we see the same piece of evidence? And we can use the Bayesian rule to make the computation a little bit easier. So we can reverse this conditional probability this way. And what we want to do is just simply compare which probability is larger, right? If this is larger, then we say, given this piece of evidence, H1 is more likely to be true. So a natural way to compare it is that we can just compute the ratio between these two. When the ratio is larger than 1, the top probability is larger. If it's smaller than 1, the bottom probability is larger. And you may ask why we want to compute the right side of this instead of the left side. The reason is that...
There's a question.
Oh, yes, please.
This is assuming we're working with mutually exclusive hypotheses, right?
Mutual, yes, right. Well, actually, with this formula, it doesn't have to be mutually exclusive. Yeah.
Okay, sorry, as a follow-up, if they're not mutually exclusive, why can't we just assign evidence to both?
Assign what?
Like, instead of deciding which hypothesis to assign evidence to, if they're not mutually exclusive, can we just assign evidence to both?
Right. Well, so yeah. Yes. Yeah, I probably got your question wrong. Yes. So here we will have to decide between these two hypotheses. So yes. So only one is true. Yes. That's right. Okay. So yeah. So before I go furthermore, I will put down some names for this term. This is what we call likelihood ratio. This is what we call bias because it describes our prior knowledge which hypothesis is true, right? And there's a reason I want to have the right form. I want to have the equation on the right side of equation is that if we consider the question that we do not just have one piece of evidence, we have a lot of evidence, many pieces. This can be conveniently rewritten in this form, right? If these pieces of evidence are mutually independent, then I can just simply rewrite this with the multiplication of multiple evidence, right? So you notice this is on the left side of the condition. If it's in this form, you cannot do this, right? So this is why we want to use the Bayesian rule to reverse this into that. And furthermore, we can compute the log of the top thing so that we can convert the multiplication into addition. And then we have another name for that. We call log likelihood ratio. Okay, so now coming back to this. In DDM, we accumulate evidence in this form. Now we know that when we have the actual evidence, we can do the summation of the log likelihood ratio, just very similar to how we form the DDM model. And that's what we call the sequential probability ratio test. So in sequential probability ratio test, everything is very similar to DDM. The only thing is now we know exactly how much each piece of evidence is worth. So when we receive some evidence, we compute the log likelihood ratio, we add it to the accumulated evidence until we reach a bound. And when the bound is reached, we will make a decision accordingly. And so the evidence is just the log likelihood ratio that I introduced. And this sequential probability ratio test is first proposed by Abraham Watts in 1945. And he also showed that the SPRT happened to be the test that can help you to reach the fastest decision given the accuracy you want to have. Okay, so any question regarding to this? No? Okay. So now we have this test. The next thing we want to know is that whether the brain actually does this. Do we compute log likelihood ratio in the brain or not? So I'm going to show you a bunch of studies to prove that. Well, last time I talked about the random dot experiment. But that experiment is actually not very, it's not very convenient if we want to compute the log likelihood ratio because there is a lot of noise in the random dots. And our vision neurons also introduce additional noise, which is very difficult to measure. So just based on the sensor input, it's not very easy to compute the evidence. So we want to design a new task. And with this new task, we want to show that first, the brain computes log-likelihood ratio, and the second, the brain does SPRT. And the new task is what we call probabilistic reasoning or probabilistic inference. So what exactly is probabilistic reasoning? I will give you an example. I don't know. So I will first show brain computes log-likelihood ratio. Okay, so I don't know how many of you follow soccer, and if you do, you will know that tonight there is a very important game. It's the final of the Euro Cup 2024, right? If you don't, that's still okay. So the final will be between Spain and England, and many would wonder who will win, right? So to make that prediction, you will need many pieces of evidence. Like some evidence are in favor of the Spanish team will win, some evidence are in favor of the English team will win, right? And you will notice that none of this evidence can tell you for sure which team will win, right? Even Spain has won the Euro Cup 3 times, that doesn't mean the team will win again. And some evidence are stronger than the other. Some evidence are pretty weak. So like the Spanish team is younger, that means they are more energetic, that may be in favor of Spain. But that also means the Spanish team is less experienced, maybe. So there seems to be a weak piece of evidence in favor of Spain. So that's what probabilistic reasoning means. You have a lot of probabilistic evidence, and you want to combine everything together. And so how do we solve this problem? So, as I just mentioned, we can compute the log-likelihood ratio for each piece of evidence and add up all the evidence we collected together to make the best decision possible. And we want to study this in monkeys. So we want to train monkeys to make this kind of predictions. Okay. I guess I can skip this. It's basically say, I want to say if you have this piece of evidence, you want to calculate what's the probability of, in the case of Spain will win, this player is playing, so on and so forth. And that's my favorite player on the Spanish team. And also, by the way, I support the Spanish team. Okay. Okay, so I want to train the monkey to do this task. And of course, the monkey has no idea of soccer, right? We cannot just show monkey soccer games and ask monkey to make predictions. So the way so the behavior task we train the monkey to do is actually like this. So we will show monkey 2 color targets, and we ask monkey to make choice between these 2 color targets. And the evidence we show the monkey is a bunch of shapes. And we train the monkey to learn that how much evidence is contained in each shape. And the monkey has to combine all these shapes together to make a decision. So that's very much like the example that I just showed you. You can consider that the red brain are 2 teams and the shapes are just the evidence that we collected. And in the task, the monkey just has to first look at an empty screen, then 4 shapes come on one by one. In the end, the monkey has to move its eyes to choose between one of the 2 targets. So the mathematics like this. We assign weights to each shape, and the total weights of 4 shapes in each trial would be the log-likelihood ratio that I just talked about. So if the red target is the correct target, what's the probability seeing this combination of shapes, and so on and so forth. And you can see because this term is on the top, that means positive numbers is associated with the red target being the correct target, right? And if the weight is larger, that means that's a stronger piece of evidence. If the weight is infinite, that means if that shape appears, the material will be certain that red is the correct target. Okay, and on the other hand, the green shapes what supports the green target. So, if the total log likelihood ratio is very large or very negative, then the task is really easy. There's a lot of evidence for the monkey to be sure which target is the correct target. But if the total log likelihood ratio is close to 0, that's a very fuzzy evidence, and the task will be hard. If the monkey understands statistics perfectly, that's what they should do. In a trial, suppose the monkey sees 4 shapes. They should first convert the shapes into the weights that we assign to the shapes and add them together, 0.2 in this case, and then convert this back to the probability. So 0.2 means the red target will have 61% of chance of being correct. So the monkey should choose the red target. And the important thing is that even if the monkey makes the correct choice, he still has 39% chance of being wrong, right?
Do you present all of the shapes together, or do you present them sequentially?
One by one, sequentially, yes.
How long technology for the this association with shape?
Yeah, right. It does take a long while, so around 1 year to.
I think for me, it's very hard to remember.
Yeah, yeah, but I'm sure if you do this task repeatedly for a year, you will be perfect. You will be. Yeah. So first of all, we want to make sure that the monkey does learn the task. And here we're just plotting the monkey's choice, the percentage of red choice versus the log likelihood ratio. So if the log likelihood ratio is positive, that means the red target is the correct target. And you can see the monkey almost chooses the red target 100% of the time, vice versa.
Sorry, this is a detail, but I'm curious about that last point.
Right.
How long does it take to get the animal up to, let's say, like 80% and then 90%? I asked Yanni this question many years ago, and he said that long training time is associated with very high accuracies, and so that most of the time, training the animal was going from, 95% to 97% or something like that. So I'm just curious, like, why so long, or what is they're smart supposedly, right? So
yeah, right. So first of all, the task is very hard in the sense that you cannot reach 97% forever, right? Because a lot of cases, the evidence is fuzzy. So even if the monkey is correct, we still don't give the monkey a reward. So the monkey can never be certain what is correct, what is wrong. And that's the major reason we believe why it takes the monkey so long to figure out the task. Actually, we train the monkey step by step. So in the first stage, we just train the monkey with single piece of evidence so that the monkey can get an idea of what's each single piece of evidence mean. Then we start to mix shapes together, train them by one. And the longest it takes is the first stage and the second stage. So the second stage is when we put 2 shapes together, and the monkey has to get the concept of how to combine these shapes together. And once past that stage, when we add the third and the fourth shape, actually the monkey is pretty quick to get the idea.
How many shapes you show sequentially?
4 in this experiment, but later I will show more.
Do you see any recency bias?
Reason, no. In this case, the monkey is super well trained, so there's no recency bias.
All the shapes are displayed together, right?
Yes, in this particular experiment, we show the shapes one by one, but the shape never disappears, so the monkey doesn't have to remember them. Yeah. but we've done other versions. Actually, the monkey can do them very well as
Just briefly,
Sure.
how similar are the monkeys? I know you only had a couple monkeys, presumably, it's hard to have monkeys and stuff, but like, are they super variable in terms of what stage takes longer, or they're kind of consistent between animals?
They are kind of consistent, yeah. Actually, we've done several experiments related to this task, and we have trained probably 8 or 9 monkeys on some variation of this task. They can all learn the task. Right. So, okay. So.
Is the probability we give the monkey reward calculated by the basic?
Say again. Sorry.
Is the probability we give the monkey reward calculated by the basic equation?
Yeah, so the probability of reward is determined by the total weight of this shape, and that's the log likelihood ratio, right? So so you can say it's computed based on Bayesian, yeah, right. So we can also find out how much influence each shape is on the monkey's choice by doing a logistic regression. And the nice thing is that the logistic regression coefficient correlates with the shape weight we assign to these shapes very well. So we know that not only the monkey knows the total weights, the log likelihood ratio, and the monkey knows the weight of each single shape very well. Okay, so now we see the monkey can do the task. The next thing is we want to ask how neurons do, right? And for this task, again, we go back to LIP. So I've introduced LIP last time. LIP is involved in planning eye movements toward a particular target. And again, in this experiment, we ask monkey to use eye movements to do the task. So we think LIP would be an appropriate area to look at. So before I show you any plots, I want to give you guys some idea of how this neuron would respond during the task. Here I'm going to show some short movies of what the monkeys see during the task. You will see there is a central fixation point and several shapes will pop up in the center. And you will also see 2 targets, the red and green on the screen. And here is the response field of the neuron. So whenever the monkey is going to choose the target in the response field, the neuron is supposed to have a lot of spikes. Okay, and in the movie you will also see a little yellow dot indicates the monkey's eye position. And okay, let's see the movie. Okay, so red and green target. So in this case, the red target is in the response field, meaning whenever the monkey chooses the red, the neuron should be active. Okay. 1, 2, 3, 4. The monkey chooses red. Okay. So to help you to understand this task better, down below, I plot the log likelihood ratio for the target in the response field. So we call this T because it's in the response field. So at the very beginning, when the first shape appears, the log likelihood ratio is actually below 0, meaning it's in favor of target outside. But after the second, third, the fourth target, the log likelihood ratio becomes more and more positive. So in the end, the evidence is strongly in favor of this target. And here, these short bars are the spikes of the neuron that we recorded when the monkey is doing the task. And you can see clearly as the evidence accumulates, the neuron spikes become more and more dense. It's becoming more and more active. And in the end, when the monkey chooses the red target, the neuron is super active. So that's what you would expect from what an NLP neuron does. And we can see an opposite case. When the shape, wait, the that's the same with me. Back to the second movie. So in another case, the monkey in the end choose a green target that's outside the response field, right? And you can see these four shapes increase, well, the log likelihood ratio for the green target increases. That means the total would become more and more negative in this case. And the neuron's response also becomes lower and lower. So that's also expected. The third movie I want to show you is a little different. So in this case, the first three shapes increasingly provide evidence pointing to the green target in the response period. But the very last shape actually suddenly reversed the whole thing. Now the evidence becomes negative. That's the evidence for the red target, right? And the monkey eventually chooses the red target. And you can see this LIP neuron, it first increases the firing rate. But when the fourth shape appears, the firing rate just suddenly shuts down. The firing rate also reverses. So what does that mean? That means if I do not know what the monkey is doing, just by examining the activity of this neuron, I know exactly what's going on in the monkey's head. The monkey is thinking green, 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 then oops, red, right? So by looking at this neuron, we know the decision-making process.
So during the incubation, I'm wondering, monkey is actually looking the red dot or not? Because if the shape is a pair, I will focus the shape, not the visual field.
Yes, the monkey initially is looking at the center, at the shapes. The monkey is not looking at the target. So here the response means the monkey is planning an eye movement toward that target. Okay. And that's the interesting part. So here the monkey does not know yet what eventually the outcome is, but nevertheless the monkey is planning. And the decision for this eye movement is forming. That's what we mean, the process of decision making. Okay, the final example is just the opposite. So initially the evidence is against the target in the response field, so you see a decrease in the response. And the final shape would totally change the trend, and now the neuron becomes very active.
You start off with a minus infinity shape, and you end off with a plus infinity shape. Is there a bias to if you start off with a minus infinity shape and end off with a plus infinity shape, is there a bias towards one of the decisions?
Yes, it's a very good question. So I kind of gloss over how the infinity shape works in this text. So in our design, the infinity shape can actually cancel against each other. If in one trial you see one minus infinity shape, one plus infinity shape, they can cancel each other out. So that means the infinity are not really infinity. And when we're doing logistical regression, we can see that monkey are also not treating them as infinity. They're just treating them as shapes with very large weights. So
it does cancel out in the behavioral.
Yes. Okay. So now we can do some. Now I can share some quantitative analysis. So here I'm showing the PSTH, so the response against the time. And at the very beginning, when the first shape as well as the choice target appears, you can see a transient response. But let's ignore this for a moment. After this transient response, we see the response of the neurons diverges according to the evidence contained in the first shape. So here we have 5 traces. These are all trials sorted by the evidence, the log likelihood ratio. So more positive is the darker trace, more negative is the lighter trace. And that trend continues when we show the second, the third, and the fourth shape. If the evidence keeps growing, you'll see the accumulation of evidence in this neuron. If the evidence is going toward the negative side, you see decrease of response in the neuron. And in addition, we can compute the response of these neurons in the time window roughly around here, because we don't want the part when the shape is just on this some transition response. So we're looking at the relatively stable response period of this neuron. And we can plot the response of this neuron against the log likelihood ratio contained in these shapes, and it gets a pretty nice linear relationship, meaning that the neuron's response really encodes the log likelihood ratio in this case. And we can do this for all 4 epochs. So here, in the first epoch, again, because the initial huge transcendental response, this response versus evidence relationship is not as nice. But if we look at the rest of the 3 epochs, you can see here there are only 2 shapes. Here there are 4 shapes. But regardless how many shapes are there, the relationship between the response and the log likelihood ratio seems hold. So the number here is the slope of the fitting line. So the fact these slopes are essentially the same, meaning the neuron maintains a stable encoding of evidence across the accumulation.
Is there a difference here between preparatory motor activity and evidence accumulation?
Well, in this experiment, there is no difference. Yeah. Okay.
It's kind of look like a sigma, you know? Should it be a sigma? It doesn't.
Yes, yes. Yes, it does look like a little bit, yes. And we think it might be the case that the monkey, well, with the soluble log likelihood ratio is too large, and the monkey and the neural response becomes saturated in this case. But I want to.
This relates to your question. You see adaptation. So if you have like a set of shapes where you manipulate the range of the likelihood.
I haven't done this yet. I don't know. Yeah. So there's actually a caveat in this behavior design. So the caveat is this: it's probably not obvious to you that the shapes as evidence are not independent. So the way we do experiment is that in every trial, we show 4 shapes, right? All 4 shapes are chosen randomly with replacement. And in the end, the computer decides whether the red or the green is a correct target based on the total log likelihood ratio. But I mentioned in SPRT, the evidence, so the probability of, so the conditional probability of this evidence should be independent. In this case, it's not. It's independent only in the sense of you don't consider the outcome. If you consider the outcome, they are not independent. You can imagine if the outcome is red, okay, that's the part, that's a condition part. If the outcome is red, and you see the first evidence is in favor of the green, then the following evidence has to be red, right? Because you already know the outcome is red. So the first evidence actually would, the first evidence actually would affect the following evidence. So it's not totally independent, but we can still calculate the log likelihood ratio. So when we calculate the log likelihood ratio, we see this perfect relationship. But if we ignore this interaction, we're just adding weights together. What you get is not the true log likelihood ratio. It's just the weight of this shape. you will not get this. So that means the neurons are not just doing single addition. It's really following this rather complicated calculation of log-like operation in the brain. Okay. So in this version of the task, which is asking monkey to accumulate evidence across all shapes, it's not exactly SPRT yet. There's no bump related, and there are other things I just introduced, saying that monkey is not doing simple accumulations.
Can you summarize the PowerPoint one more time? So you're saying that the monkey basically is matching like the stimulus over time the monkey's brain learns to approximate the true stimulus generation process,
Yes.
which is like not fully independent because the outcome determines the stimuli.
Right.
Okay.
So then we move on to change the paradigm into a reaction time version. So that in the reaction time version, now the design seems to be quite similar to the previous one, only that the shape will disappear, the shape will appear one by one until the monkey is ready to make a decision. So the monkey would decide how many shapes they want to see, right? And each shape would appear for only 250 milliseconds, so the monkey can do the task really fast. And that's a key part. So previously I mentioned the dependency between the evidence, but in the new experiment, we don't want that. So we want to make sure these things are independent. And the way we do this is that we will first let the computer to pick which choice will be the correct choice. So let's say if the target A is the correct choice, then the computer would sample this shape according to the distribution associated with target A. So in this manner, we make sure that the shapes appear independently. And the log likelihood ratio is exactly the difference between the two distributions. The probability of, let's say, the red bar is the conditional probability of target A is correct and this shape appears versus target B is correct and this shape appears. Okay, so now the evidence is truly independent and you can add them up to compute the log likelihood ratio. Okay, so again, first of all, we want to make sure the monkey can do the task, and this is very similar to the figure I showed you. The monkey's choice depends on the total log likelihood ratio.
Question is how do you enforce the reaction time? There is more reward if you respond fast.
No, there's no more reward. It's just the monkey saves time and energy when they respond faster. Actually, what we often have to do is to stop monkey from responding too fast. Yeah. So we have some timeout penalty if the monkey is making too fast a response and wrong. Okay. Sure.
I had a related question. Is that what is fixed is the number of trials or the duration?
What do you mean? What is
in an experimental block? What is fixed is how many trials, how many decisions the monkey makes, or the duration.
Well, neither is fixed. So in each trial, the monkey gets to decide how many shapes they want.
No, that's not my question. My question is, in a block, how many decisions are there?
Yeah, well...
Is that fixed or the duration of the block?
It's not fixed. The monkey decides the pace, right? The length of each trial is not determined, and the monkey typically stops by the time they get enough juice reward. So it's not predetermined how many tries they can do. Okay, so the next thing we want to show is that the monkey does stop at a threshold, right? So here, the x-axis is the number of shapes the the monkey used in their decision. So it varies from 2 to 10. So sometimes the monkey would view up to 10 stimuli before they make a decision. And the x-axis is accumulated evidence for each case. And you can see no matter whether it's just 2 shapes or 10 shapes, the total accumulated evidence seems to be pretty much the same. So, so these are for 2 choices, right? In one choice, the total evidence is positive. In the other choice, the total without evidence is negative. Okay, so just from the behavior, it looks like the monkey is really doing something like SPRT.
Yeah, so just a question on the time effect. So, I mean,
so could one imagine the optimal strategy is to guess as fast as possible, and then you go through a lot of trials and then get more reward rather than waiting for the evidence?
Right.
So just how to prevent the monkey doing something like that?
Yes. So we would give you the monkey a long time out if they are making fast but wrong responses. So the optimal strategy wouldn't be do the test very fast, right? Okay, yes, that's a very good question. Okay, so again, when we examine the LIP neurons, we see this pattern. So the responses diverges as more and more shapes appear. Positive evidence lead to increase of the neuron response, and the negative evidence lead to a decrease of responses across time. So here we show 5 epochs. And again, if we plot the firing rate against the log likelihood ratio, you see a pretty stable encoding of log likelihood ratio across time. And again, I want to emphasize here, the log likelihood ratio is just a simple addition of the log likelihood ratio associated with each shape, unlike in the previous test. And nevertheless, the monkey, the neurons follow the log likelihood ratio perfectly. Just, please.
did you change the delay between, so did you have a case where you have longer delay between
Did you have a case where you have longer delays between the presentations?
Well, for the neural data, we don't. But for the behavior, we did test a range of delays, and that turned out does not affect the monkey's behavior very much.
So they continue to remember?
Yes.
And so there's also no recency bias in this?
There's no recency bias. Yeah. Well, there's some caveats. For example, the last shape, the very last shape, could perfectly tell you the monkey's choice. And the reason is that if you consider SPRT, right, you have to accumulate evidence to cross the bound. So the last shape would always cross the bound in the correct direction. So the last shape would tell you the monkey's choice perfect. So in our analysis, actually, we got rid of the last shape. But that's actually the evidence for SPRT, right?
Yes. Might be a stupid question, but like, if I don't use the log likelihood, I just use the sum of the negatives, I still can get somehow a positive correlation or negative correlation. Right. And then I can, like, for my readout neurons, I can have another form that's kind of, so my question, like, basically is why we need a linear between the log likelihood and this neuron's response. I don't, yeah.
Yeah, so here, so again, when we compare this experiment with the previous experiment, so in previous experiment, if you just simply add up the weights associated with each shape, that's not the true log likelihood ratio because they are correlation. So you have to discount the later shapes. And after 10 days, you compute the correct log likelihood ratio, you still get this relationship. So that means the neurons are not just simply adding these shapes together, they are really computing the log likelihood ratio. So in this experiment, the two things are the same. You're just adding things up. Right. Okay. Okay, so on the other hand, by the time the monkey is making a choice, you can see all the choices converge together, as would be the case of SPRT. So here we're computing the slope. So the slope are just basically the response under different evidence conditions. So larger slope means more difference between these traces. And you can see the slope gradually decrease towards zero before the saccade happens. So that means the difference between these traces becomes smaller and smaller until roughly around here before the saccade it reaches, it converges to a threshold. Okay.
This means that it has a fixed threshold and not collapse.
Yes. In this case, the monkey does have a fixed threshold. Yes. Okay. So by now we've shown the evidence that LIP neurons do encode log-like ratio during evidence accumulation, and they do behave as what SPRT would predict. So the DDM that I've shown you in the last talk may be well captured by the SPRT. And in SPRT, we have a better way to quantify the evidence that's being used in decision making. Okay, so I have about 10 minutes, but then we take one more step forward to show you the LIP can do evidence accumulation in addition to SPRT or DDM. So in this case, we make this task even more complicated for the monkey. And here, we call it multi-stage evidence accumulation. So the task now is like this. Previously, all the shapes are used for the evidence of choice between red and green, right? So in this new version of task, the monkey still sees a series shapes, actually 6 shapes now. But now the shapes have color. So if it's a red color, it only tells you the reward probability of the red target. So it provides evidence in this form. If you see this shape, what's the probability of the red shape, the red target being rewarded versus the probability of red target being not rewarded? Okay, so now this video stimuli has 2 properties that can be used for decision making. One is the shape. If it's square, that's 0.9. That has a weight of 0.9. That means you will have larger reward probability. But which target will have larger reward probability is determined by the color of the stimulus, right? And also in this setup, the reward probability of the 2 shapes are actually independent. You can have the case both targets have high reward probability, or both targets have low reward probability. And the monkey now has to accumulate evidence for both targets in this case. All right. And now again, we can show you the monkey does this. So the choice, the percentage choice of choosing red target is now the total weight of the red target minus the total weight of green target. And again, if we do logistical regression, we can show that regardless the color of the weights, red and green, they always have a nice relationship, relationship depending on the assigned weights of these shapes. So the monkey knows the weights associated with each shape. But the important thing is that this is why we call this a multi-stage accumulation task. So the monkey has to use both the shape and the color together for the decision making. And there are 2 possible ways to do that. Let's consider this particular example. So two targets, the green target is in the response field of the neuron. Okay, so now we see a red square in the center, and we know the weight of the square is 0.9. So that's strong evidence for the red target can be rewarded, right? So the shape color is red, the weight is 0.9. If we combine this together, we know that the probability of red is getting rewarded is good, right? But then we want to know if the red target is in the response field or not, right? If the red target is not in the response field, so that's actually evidence against the target in the response field. So now the evidence is negative, right? So we have to first compute this together into the evidence that can actually be accumulated. And any of these two things cannot be accumulated directly. So you need to assemble the evidence first for accumulation. But that's not the only way you can do the accumulation. We can do it in this purple route. So in this purple route, we first decide, so we first would compare what color is in the response field and what weight is. So you can compare these two things together. And then depending on whether the color of the shape and the target inside the response field is consistent or not, then putting everything together to know that the evidence is negative, right? So there are two routes to do this calculation. So when we look at the neurons, we can actually find evidence to decide how monkey actually computes this evidence in this case. So first of all, we can show that the ARP neurons are doing accumulation very similar as previously shown. You can see the fire rates correlate with the total log likelihood ratio perfectly. You can we basically replicate the previous finding. And in addition, I want to point to you this interesting transient response after the shape onset. So in this period, that's what we use to analyze. This is like the stable encoding of the log likelihood ratio. But in this period, which I ignored previously, there has a lot of interesting transient. And we wonder if this period actually would would reflect the process that the neurons are assembling evidence for accumulation. And if it does, it can tell you how the neuron assembles the evidence, through which route the neuron assembles the evidence. And the way we do this is that we use a Poisson gel in the process. So the idea of Poisson gel is that we want to decompose the neuron's response as the response for each individual event. Let's say if event A would lead to a response like this, event 2 would lead to a response of this, then we can add them together to predict the neuron's spike sequence. And I probably would have to skip these mathematical details, but in this experiment, these events are just the property of the stimulus we provide to the monkey. So we can invest things like the weight associated with the stimulus, the color consistency, so on and so forth. So first thing we want to look at is the weight associated with each shape. So remember, in this experiment, the weight is not a quantity that you can directly accumulate. You have to consider the shape color as well, right? So the left is a heat map of each individual neuron is a line, but when you're adding them together, you can see overall the neurons have a negative response to the weight. Starting from the shape onset, it's 0. So for both monkey, that's the case. There's a strong negative response for the weight, meaning that if the weight is positive, indicating loss of reward, actually LIP neuron will be suppressed. regardless which target, which color it is. And in addition, we can look at after the evidence is assembled, that's accumulate. When does this accumulation of evidence occur? You can see in both monkeys that information does not appear until shortly before 500 milliseconds. So initially, so it looks like initially the monkey is doing something about the shape weight instead of just directly accumulating the evidence. And now this is the interesting part. So previously I showed you there are two possible routes, and these two variables are the key difference between these two possible routes. So in one case, you would first decide whether the shape in the center and the target in the response field has the same color or not. And we found this information is computed only in monkey M. And the other route is which you first just compute the shape weight and shape color together to calculate the evidence for a particular shape. And this is only from the monkey edge. So we have two monkeys, and it looks like two monkeys are taking two different ways to do the computation. But in the end, both monkeys, neurons in both monkeys would encode the accumulated evidence. So now that's what we found. Previously, we know that LRT is doing this accumulation, right? And now we found the short period of transition after the stimulus onset actually reflects the calculation of putting everything together into the evidence that can be accumulated. And you can examine the neuron to find out how exactly they compute this evidence. That's not possible just from the monkey's behavior, because in monkey's behavior, all you see is the monkey using accumulated evidence to do the decision making. So only from the neurons you know how monkey actually calculates their decisions. All right. So that's pretty much what I have for this lecture. I hope I convinced you that the brain is accumulating evidence in the form of localized table ratio. That's pretty amazing, right? Because probability is actually not something that's very easy to compute, especially when you consider things like things can be correlated, things can be dependent. And secondly, we show that the DEM that many people use is actually a form of SPRT. Okay, so questions? Please.
So in your last second slide, you showed that two different monkeys probably use two different routes to do this. So can I explain, like interpret this as like one is first kind of perception and then kind of action, considers information, and the other way around. So I was just wondering if there are some kind of, say, the action files in this experimental task. Say, for example, in most of the trials, the red one would be choose instead of like half and half. Would this like change the way the monkeys consider the perception and action information? Would that switch the perception action monkey also to the way like first action and then perception?
I'm not sure what you mean by perception and action, because in both rods, actually, all these variables are not directly related to the action. So you have to put in all of them together to compute the evidence here. And only this quantity can be accumulated and it is correlated with action. All the other things are actually orthogonal to action.
Yeah, maybe I used the wrong term. It's just like your slide showing there are different orders to do so, right?
Yes.
There
are different ways to.
Yeah. Could you show the slide that you like one monkey, the first doing more responsible to the color, and the other more responsible to the weight?
Yeah, but in both ways. So the first monkey is going through the purple rod, and the second monkey is going to the blue rod.
Yeah.
And in both rods, they are not doing anything about the action initially. So this whole part is now related to action. Only the last part is related to the action, and the last part is shared by both monkeys. So I'm not sure about your question. Maybe we can discuss later.
Later.
Yeah.
Last question, how many linear, IP neuron, linear correlation neuron you find of all the neuron you recorded, and for the rest of the neurons, did you find some nonlinear encoding of that information, or other neurons are encoding random things?
We didn't examine that carefully because to determine whether a particular neuron is linear or not is actually not easy. Yes. Sorry, can't answer your question. Sorry.
I missed it. In single trials, are the changes in neural activity proportional to what you would have expected from the log-to-log ratio of each piece of evidence?
Yes, that's what I'm trying to say. Yeah. Even in the case when the computation of log-like ratio is not a simple addition.
Hi, I have a clarification question. So is this saying, because so if you see a red color stimuli, that doesn't indicate anything about the green one in your second task, right? So theoretically, you could have a combination where both options could be rewarding.
Right.
Because they're independent.
Right.
So are you saying that there are different neurons encoding the red versus green separately?
Actually, what we are seeing is that the neurons are encoding the difference between the two probabilities. So we looked at that. The neurons are not encoding only red or only green. They are always encoding the log likelihood ratio difference between red and green.
Oh, I see. Then what if you have three options?
Yes, that's a very good question, and that's also what we want to do in this design. So I remember someone also asked about the multi-alternative choice in the previous lecture, which is very difficult to do in the random dots task. And here it's relatively easy. I can just add a new color, which can be totally orthogonal to this everything. Yeah. So maybe a few years later, I can give you an answer, but we don't know yet.
Yeah, so this is very convincing work, and I mean, there's no doubt that the neurons that you're recording from is reflecting the accumulation of evidence according to the rules you put forward, but to what extent do we know that they are the neurons actually doing the job, or just what they show is that a reflection of compensations done other way in the brain?
Yes, that's a very good question and a very difficult question. So actually, part of the reason we do this task is we want to find out if LIP only does that accumulation or the LIP is doing something in addition. So if there's only accumulation signal, meaning only signal reflecting this quantity, it's very likely, it would be more likely that quantity is computed somewhere else in the brain, and the LIP just receives a copy of that quantity. But what we found is the LIP neuron is doing the whole computation, right? So to me, that seems to argue that LIP is really where all this computation happens, because if this happens at somewhere else, it's not necessary for LIP to have a copy of all the intermediate variables, right? If LIP wants to know the answer, it only needs to copy this quantity, right? So I think this experiment would argue for the role of LIP in the whole decision process, not just copying the signal from a different area. But still, that's only a correlational study. To fully answer your question, we need to do some causality experiments. But those experiments are pretty hard to do at the moment. If you do leashing and get negative results, that could have many different answers. Maybe brains have some compensation mechanism, has some redundancy in the circuitry that allow the brain to keep doing what it used to do. So there are a lot of controversies in the field regarding what exactly the LIP's role is. To me, I believe LIP is very important in this.
So just another question also. So on the coding itself, so I guess the accumulation of evidence, people in the past at least were very much leaning towards looking at firing rates. And has this been this debate to what extent brain oscillations are important for coding, right? And I guess more recently, Mike Shackland has published a paper where at least there's a role for beta oscillations. So I just was wondering, according to your view, I mean, is there also room for brain oscillations taking part, at least in some of the conversation in this framework?
Yeah, well, I'm afraid I don't really have thought a lot into this issue. The oscillation is, of course, very important, and the immense study has been shown oscillation plays a pivotal role in coordinating between different brain areas. Right now, if we only look at LIP, I'm not sure how to answer your questions, but yeah.
To go back to the first question, what happens if you inactivate LIP?
Yes. So there is a famous study that published in Nature by Alex Clark, showing that inactivating LIP actually does not do much. But as I said, negative results can have many different interpretations.
I didn't guess what you said.
Inactivation of LIP does not lead to behavior change in this type of task. But as I mentioned, the negative results can have many possible interpretations. It could be the case that the experiment, the inactivation didn't do what the experimenters thought they would do, or it could be the case that brain has redundancy that to compensate for this inactivation. And in addition, there are microstimulation experiments to show that stimulating LIP neurons does lead to change in decision making consistent with the DDM hypothesis. So I think the answer is still out there. We don't exactly know.
Thank you for the talk. So your probabilistic reasoning task is one of my favorite tasks, and after the example that you gave in the introduction is going to be one of my favorite talks from you. So I have one question regarding the log, the SPRT. So if the animal has learned very well the log likely, the log odds for each of those, so where this additional variability is coming from in the decision-making process? So I guess I'm asking,
right,
if you can compute perfectly well the log odds, then the response of the animal should be deterministic in that sense. So where this additional variability is coming from?
Yes. So yes, that's That's an excellent question. So, yes, there are a lot of details that I kind of just gloss over, but very much related to your question. Yes, so here, when we are doing logistical regression, I show you that the coefficients seems to match the shape weights very well, right? And we're using this figure to show that monkey seems to learn the quantity of each shape pretty well. But as you mentioned, if the monkey is doing a test perfectly, whenever the log likelihood ratio is positive, choose red, so on and so forth, that actually shouldn't look like this. It should be a step function. So like on this side, it should be all positive. On this side, it should be all negative. So the reason it kind of sits there is that the monkey actually has a lot of noise in its choice. Even when the log likelihood ratio is positive, it doesn't always go for the red target. It still distributes its choice between the two targets. One possibility is that the monkey is doing something called probability matching, right? So let's say if the red target is 80% correct, the monkey chooses the red target for 80%. That has been shown in many animal behavior tests in which so the animal tend to match the probability. But that's not the optimal choice, right? So the optimal behavior should be you always choose the one with larger probability. So the alternative to this explanation is that the monkey just does not calculate the probability perfectly. There's noise in the computation that lead to this. If everything sits on the diagonal, that's perfectly probability matching. It looks like the monkey is doing that, but I tend to believe that the monkey is not doing probability matching. It's just that the noise happens to make the monkey look like they are doing probability matching. Yeah.
All right.